Elon Musk is no stranger to transforming industries. He has already launched rockets that not only reach orbit but return safely to Earth, and he has overseen the creation of cars that practically drive themselves. But what if the same ingenuity that redefined space exploration and electric mobility turned its full attention to aviation? Imagine a future where planes powered by electricity lift straight from rooftops, glide silently across hundreds of miles, and touch down without burning a single drop of fuel. By 2026, conversations about such an aircraft are picking up speed. It is the sort of vision bold enough to send shockwaves through the aviation industry, forcing traditional manufacturers to scramble just to keep up. This futuristic aircraft is being imagined as something entirely new, a blend of the elegance and speed of a private jet with the flexibility and everyday practicality of vertical takeoff flight. Think of it this way: no crowded airports, no long lines at security checkpoints. It's just the ability to rise directly from your driveway or a rooftop pad and head straight to your destination. The dream is as audacious as it is captivating. But the engineering details reveal just how feasible it might be. The foundation starts with the aircraft's frame. Instead of traditional aluminum alloys that have defined aviation for decades, this new design employs carbon fiber reinforced polymers. Compared with aerospace-grade aluminum like the 2024 T3 variant, which is common in smaller aircraft, these composites reduce overall mass by roughly 22 to 27%. That weight savings isn't just about efficiency. It means more room in the design budget for larger batteries without pushing the aircraft's maximum takeoff weight beyond practical limits. Engineers orient the fibers in highly stressed zones in one direction for maximum strength, while weaving them in complex curves for flexibility. The result is tensile strengths exceeding 800 megapascals, stiffness ranging between 70 and 120 gigapascals, and an exterior surface so smooth that its roughness measures below 50 microns. Pair that with carefully designed wing-body junctions, and drag drops dramatically, achieving coefficients as low as 0.018, well below the 0.025 to 0.03, typical of comparable small aircraft. That aerodynamic improvement alone boosts cruise efficiency by 8 to 15% at speeds of around 300 kilometers per hour. The wings are equally advanced. By blending wing roots smoothly into the fuselage and minimizing interference drag, the design achieves aspect ratios between 9.5 and 10.5. The addition of winglets capable of maintaining laminar flow across nearly half the wing chord further increases efficiency. Lift-to-drag ratios soar to 17 or 18, compared with just 14 or 15 in current designs. This means longer range and better performance without having to add weight through larger batteries. Perhaps the most radical feature is the ability to take off and land vertically. Traditional runways could become optional. This is made possible by 6 to 8 vectored electric ducted fans, each capable of delivering 80 to 120 kilowatts of thrust. For a plane weighing up to 1,800 kilograms at maximum takeoff, total thrust requirements reach around 26.5 kilonewtons, which can be evenly shared among the fans. With fans measuring about 0.85 meters across and spinning at tip speeds of 250 meters per second, vertical lift becomes not only possible, but reliable, even in thin, hot air at high altitudes. The experience promises quiet efficiency as well. Noise levels would remain below 65 decibels from 100 meters, away, about 25 decibels quieter than a helicopter. This is achieved through the enclosed ducted design, acoustic tuning between stators and rotors, and variable pitch blades. At the heart of each fan are permanent magnet synchronous motors, reaching peak efficiencies above 94% and using magnets stable at high operating temperatures. A liquid cooling system circulates fluid through microchannels and cold plates, preventing overheating during the intense bursts required for vertical flight. Durability is also woven into the design. Instead of open propellers, which pose hazards and are prone to wear, these fans are housed within carbon fiber structures reinforced with honeycomb cores. Not only does this add protection, but it improves static thrust by 12%. To manage all of this complexity, a redundant central flight control computer operates hundreds of times per second. directing thrust, vectoring with split-second precision. Of course, all this is only useful if passengers enjoy a safe and comfortable ride. That's where the cabin comes in. A compact 4-seat electric plane might have an internal width of 1.4 meters, a height of 1.22 meters, and a length of 2.8 meters, producing nearly 5 cubic meters of gross cabin volume. Once you account for structure and systems, the usable space is about 3.4 to 3.8 cubic meters, roughly 1 cubic meter per passenger. Heavy batteries sit beneath the cabin floor, lowering the center of gravity by up to 15 centimeters compared with traditional designs. This improves roll stability and makes the ride smoother. Even in turbulence, seats are designed with automotive ergonomics in mind, offering widths between 48 and 52 centimeters and generous spacing between rows. Cushions balance comfort and weight, using medium-density foams thick enough for long journeys while keeping individual seat weights under 18 kilograms. Some designs even allow reclining up to 150 degrees. Though this requires sturdier frames at the front, a single touchscreen becomes the hub of interaction, handling navigation, systems monitoring, entertainment, and even cabin climate. It responds instantly. But aviation regulations ensure that essential flight controls remain backed up by physical switches and levers. Storage space is thoughtfully designed, with compartments at both the nose and tail able to carry a combined 2.1 cubic meters, enough for large luggage or sporting gear without compromising the aircraft's balance. Loading heights stay low, making it practical for passengers to handle cargo themselves. Even on rooftop pads, noise and comfort are carefully managed as well. Electric propulsion changes the vibration profile compared with piston or turbine engines. But through active dampers, insulation layers, and enclosed fans, cabin noise remains under 55 decibels, during cruise quieter than many household dishwashers. Heating and cooling systems draw between 1.5 and 3.5 kilowatts during flight, with short bursts of higher power while on the ground. At altitudes below 12,000 feet, no pressurization is needed, simplifying systems and keeping weight down for higher altitude flight. Stronger structures and more powerful systems add weight and energy demands, presenting a design trade-off. Energy storage becomes one of the key challenges. Consider an example. Cruising at 300 kilometers per hour for 150 kilometers requires about 97 kilowatts of energy. Add reserves and vertical takeoff requirements, and the total climbs to around 125 kilowatts. With today's battery densities of about 260 watts per kilogram, this equates to nearly 500 kilograms of batteries. Doubling the range doubles the required battery weight, highlighting why efficiency and advanced chemistries are essential. Designers must choose between shorter ranges suited for urban hops or heavier hybrid approaches for longer. Safety is engineered into every aspect. Seats are mounted on energy-absorbing tracks that withstand crash forces 16 times greater than gravity. 4-point harnesses keep passengers secure. Batteries sit in reinforced compartments equipped with fire suppression systems and vents that redirect heat away from the cabin. Electrical circuits are split into independent subsystems with protections against overcurrent and overheating. Flight software and hardware are developed to meet rigorous standards like DO-178C and DO-254, while environmental durability follows DO-160 protocols. Even routine maintenance is streamlined. Electric motors require far fewer inspections than combustion engines, while modular battery packs can be replaced piece by piece instead of as a whole when it comes to durability. This aircraft goes far beyond traditional light planes. Instead of relying on aluminum alloys with tensile strengths around 470 megapascals, the structure uses a proprietary stainless steel-based alloy engineered to exceed 1,000 megapascals. With densities similar to aluminum, this metal resists dents and damage from everyday handling or airborne debris, extending the aircraft's lifespan and reducing repair costs. To further protect the exterior, engineers apply a polymer coating embedded with microscopic capsules. When scratched, these capsules release a liquid that hardens in sunlight, repairing up to 80% of the damage within 24 hours. This self-healing surface not only keeps the plane looking sleek, but also prevents small imperfections from adding. Aerodynamic drag that the propulsion system also emphasizes longevity. Permanent magnet synchronous motors are coated with heat-conductive epoxies, cooled by liquid flowing through microscopic channels, and designed to run more than 10,000 flight hours without major service. With efficiencies above 94%, these motors waste little energy as heat and avoid the gradual wear and tear of traditional engines. For operators, this means fewer oil changes, fewer spark plug replacements, and far less downtime. Put it all together, and this electric aircraft blends lightness with resilience, innovation with practicality. Its structure is stronger, yet no heavier than traditional planes. Its skin can heal itself from scratches, and its motors deliver years of reliable performance with minimal maintenance. The result is a flying machine that doesn't just meet the expectations of aviation, it reshapes them. The broader employee